Então, boa tarde a todos. É um prazer enorme a gente estar abrindo aqui o Simpósio Brasileiro de Banco de Dados, na sua edição de 2021, o CADEMAIO 2021 também, né? A gente tem que contextualizar um pouco o cenário que a gente está. A expectativa nossa é que o Simpósio Brasileiro de Banco de Dados fosse realizado em Búzios esse ano, de forma presencial, mas dessa vez a gente teve que manter ele na forma virtual, usando a plataforma Zoom. Então, lá por volta de março desse ano, né, então, eu recebi uma ligação do Fábio me avisando que tinha um problema, e aí o problema é que o SBBD deveria ser realizado de modo virtual, né, e ele perguntou se a gente podia tocar essa iniciativa. E, normalmente, eu não curto muito esse tipo de cenário, mas, dado que o Fábio me pediu, então não tive como negar. As únicas condições que a gente pediu foi que o evento tivesse uma estrutura razoavelmente simples e de baixo custo. Então, a ideia de usar o Zoom e ser bastante dinâmico nesse cenário foi uma questão que a gente considerou importante. E aí, a gente queria agradecer ao Sérgio Lisifit por ter disponibilizado o Zoom da PUC para viabilizar o baixo custo e tornou acessível as inscrições das pessoas, né, para poderem participar do evento. E a outra condição é que eu precisava de alguém mais comigo para poder tocar o projeto, tinha que ser pessoas assim, de excelência, e nesse caso tinha que ser ou Rafael ou Bezerra. E aí, no caso, eu fiz o convite inicialmente para a Rafael e, felizmente, ela aceitou. Posteriormente, o Luiz, do CADEMAIO, também entrou em contato com a gente, pedindo apoio local para conduzir o processo do CADEMAIO integrado com a SBBD, e aí a gente fez o convite para o Bezerra, né, tocar essa empreitada. Então, de fato, era o cenário ideal para a gente conduzir esse processo. A gente gostaria de agradecer também, nesse momento, os patrocínios que a gente obteve da Logi e da Meliu. A gente pede para quem puder entrar no site do SBBD e visitar lá os estandes virtuais que a gente disponibilizou. E agora eu gostaria de passar a palavra para a professora Rafael Coutinho.
Boa tarde, pessoal, né? Sejam bem-vindos aí oficialmente, né, ao Simpósio Brasileiro de Banco de Dados. Falando um pouquinho, né, do número de inscritos até o momento no evento, a gente recebeu cerca de 260 registros, né, assim, entre a pagar, confirmados, né? Então, até o momento, a gente tem 212 inscrições confirmadas, né? Então, acho que um número relativamente bom, né, para esse momento nosso. Além disso, a gente gostaria de incentivar o pessoal aí a participar, né, das palestras que a gente vai assistir. O Eduardo comentou, né, dos nossos patrocinadores. A gente vai ter palestras com representantes de cada uma das empresas. Então, para incentivar o pessoal a também fazer perguntas, a gente vai fazer premiações, né, das melhores perguntas aí nessas palestras. No caso das palestras com as empresas, serão as 3 melhores. Além das palestras com os patrocinadores, a gente também vai ter os painéis. Hoje, logo depois, né, no final do dia, a gente vai ter o primeiro painel. Então, também vai ter premiação para esse painel aí, no caso, a melhor pergunta, né, feita aos participantes, aos apresentadores. Na sexta-feira, a gente vai ter o segundo painel, que é o painel envolvendo as empresas, né, da Log e da Melius. Então, também vai ter premiação. E, além disso, vai ter a premiação nos nossos Keynote, né? Começando hoje, o nosso primeiro, depois seguindo na quinta-feira e na sexta-feira também, com a melhor pergunta da sessão. Então, gente, sejam bem-vindos, né, mais uma vez. Eu acho que eu agora passo a palavra para o Eduardo Bezerra, né, que vai falar um pouquinho sobre o CADEMAIO.
Muito obrigado, Rafael. Boa tarde a todos. Eu também me falar bastante rápido, são alguns agradecimentos e um convite. Começar a agradecer ao próprio comitê diretivo da SBBD por ter aceito ser o anfitrião do CADEMAIO nesse ano. Então, se facilitou sobremaneira a tarefa de organizar o CADEMAIO. Qualquer um que já ajudou na organização de um evento, seja grande, seja pequeno, sabe o quão hercúlea essa tarefa de organizar um evento. E essa integração com a SBBD esse ano foi fundamental para a gente facilitar a nossa tarefa. Quero também agradecer ao Comitê Diretivo do CADEMAI pela confiança de, nesse ano, participar como organizador local do CADEMAI. É uma tarefa bastante desafiadora, mas a gente sempre aprende bastante e aumenta as nossas colaborações. Foi uma experiência bastante enriquecedora. Em particular, eu gostaria de agradecer aos membros mais próximos do Comitê Diretivo, o Luiz, mestre da Federal de Lavras, ao Moacir Ponte, da USP, e ao Diego Silva, da UFSCar, que trabalharam mais próximo comigo na organização do CADEMAI. E também, não menos importante, aproveitar para agradecer também aos voluntários, tá, Jéssica? Deve aí esse agradecimento para os voluntários, que sem vocês a tarefa também seria impossível de realizar. E, por fim, convidar a todos a prestigiarem as atividades do CADEMAI. Hoje de manhã nós iniciamos as atividades do CADEMAI, já teve uma sessão técnica, já teve também a primeira, de um total de 2, já teve uma primeira palestra convidada, temos mais uma segunda palestra convidada e mais 3 sessões técnicas. Então, fica aí o convite para vocês participarem das nossas atividades também. Muito obrigado.
Então, a gente passa a palavra agora para o professor Maurício Mota, diretor-geral do Centro Federal de Educação Tecnológica, Celso Costa da Fonseca.
Obrigado, Eduardo. Meu boa tarde a todas e todos. Queria iniciar parabenizando aos organizadores, né, do SBBD 2021, CADEMAI, aqui representando o agradecimento através e parabenização através do Eduardo Ogazawara, Eduardo Bezerra, a professora Rafael, estendendo a todos, né, que organizam os 2 eventos. A gente sabe dos desafios, né, desse momento crítico, né, mundial da pandemia, mas ainda assim soluções, né, vêm sendo buscadas e apresentadas, né, para que a gente dê conta, né, das questões da pesquisa, do ensino, né, e da extensão, aí falando aqui no caso do nosso Cefet. Então fica aqui o agradecimento de estar participando dessa abertura, né, o Cefet como um dos organizadores, junto com a SBC. Só uma pequena apresentação para quem não nos conhece, né, como instituição pública. O Cefet é uma instituição centenária. Nesse ano nós completamos 104 anos. Desses 104 anos, hoje o Cefet, há uns 10 anos, teve um expressivo crescimento, né? Hoje nós estamos em 8 campi, né, em torno aproximadamente de 20 mil alunos. A origem do Cefet vem dos seus cursos técnicos e das engenharias, né? Então, hoje o Cefet apresenta 33 cursos de graduação, 12 cursos entre mestrados e doutorados e 35 cursos técnicos, né? Como eu falei, a nossa origem vem das engenharias, mas na área de ciência da computação hoje se apresenta com a segunda maior área do Cefet RJ, né? E mais do que a questão de cursos e alunos, eu queria deixar aqui registrado também, né, a qualidade do trabalho apresentado pelos docentes, né, do Cefet nessa área de ciência da computação. Hoje nós temos 4 graduações nessa área, né, 5 cursos técnicos e um mestrado. Essa área, para nós, é uma referência através da Escola de Informática, né, que consegue promover a verticalização do ensino na área da ciência da computação. É uma referência, inclusive, para os cursos mais antigos nossos, né? Então, fica aqui o registro, estou vendo aqui o Ogazawara, o Bezerra, né, que fazem parte da Escola de Engenharia, como também a nossa atuação plena dessa área com os nossos parceiros internacionais, que eu não posso deixar de citar, né, experiências extremamente exitosas na oferta de cursos através da Escola de Informática para as universidades parceiras nossas nos Estados Unidos, né, e com extremamente bem avaliados esses cursos pelos alunos americanos. Quer dizer, e a cada dia essa área vem se mostrando com ações de extremo interesse para o desenvolvimento da cidade, né, no mundo do esporte, da saúde, né, ou seja, transpondo os muros do Cefet, né, através da possibilidade, seja de extensão ou desenvolvimento, né, de processo, em benefício da própria sociedade. Então, fica aqui o meu registro extensivo a todos da área, mas em específico também aqui, olhando como representante do Ogasawa Bezerra, né, que eu acompanho bem mais de perto pelo Cefet, da importância da área, né? Então, eu não vou me alongar mais, mas desejar um evento de sucesso, né, a todos os participantes. Fica aqui um abraço do Cefet. Estamos de portas abertas nesse momento ainda virtual, né, seja o abraço ou as portas, mas nós somos otimistas, temos certeza que em breve estaremos abrindo realmente na forma presencial para receber a todos que assim quiserem nos visitar. Um grande abraço a todos. Obrigado.
Obrigado, professor Maurício. Então, a gente gostaria de passar a palavra para o professor Ricardo Torres, que é o coordenador do Comitê de Programa do SBD 2021.
Bom, muito obrigado a todos. Boa tarde. É com muita alegria aqui que eu faço parte dessa sessão de abertura. Eu aproveito para cumprimentar os membros aqui dessa mesa virtual. Inicio cumprimentando o professor Maurício Mota. Obrigado pela oportunidade de interagir com o Cefet e contar com o apoio do Cefet, e principalmente da dedicação do Eduardo e da Rafael nesse processo de organização do SBBD 2021. Eu agradeço também a confiança, né, do Eduardo Bezerra e a parceria com o Cademaio. Então, muito obrigado. Sejam bem-vindos ao SBBD 2021. Eu cumprimento de maneira entusiasmada todos os presentes, todos aqueles que estão comprometidos com essa comunidade. Trata-se da segunda edição virtual por conta dessa situação de pandemia. Isso nos fez lidar com uma série de desafios de como fazer networking, brainstorm, como coordenar, organizar e realizar este evento, partindo de encontros, em sua maior parte, de forma virtual. Como se trata de um segundo evento, realizado no formato digital, ele se beneficia do aprendizado obtido da edição anterior, então registro também agradecimento ao professor Sérgio, da PUC do Rio, pelo apoio. E esse aprendizado nos fez organizar o SBD 2021 de forma que ele se estabelece como um evento plural, diverso, repleto de oportunidades para fortalecimento do diálogo e troca entre os membros da comunidade e o estabelecimento de pontes com a nossa sociedade. Nesta edição, nós temos 2 minicursos, 3 tutoriais, um Dataset Showcase Workshop, workshop de teses e dissertações, workshops de trabalho de graduação, sessão de demos, concursos de teses e dissertações, painéis, palestras de empresas convidadas, 11 sessões técnicas para apresentação de artigos longos e curtos, incluindo artigos de destaque publicados por membros da comunidade em veículos internacionais, apresentações de palestrantes internacionais e nacionais tratando de temas relevantes do estado da arte relacionados aos desafios de gerenciamento de grandes volumes de dados, principalmente temas que tocam questões de integração de dados, integração de diferentes comunidades, como banco de dados e aprendizado de máquina. Todos estes eventos foram concebidos, organizados e vêm sendo realizados a partir do trabalho, dedicação e esforço voluntário de vários membros da comunidade. Então, eu agradeço fortemente todos os coordenadores de sessões, revisores, autores dos trabalhos aceitos, dos trabalhos que, porventura, não puderam ser apresentados. Agradeço novamente os organizadores locais, Eduardo e Rafael, os membros da Comissão de Banco de Dados pelo apoio e por todo o trabalho de bastidor que a gente vem fazendo, a Sociedade Brasileira de Computação pelo apoio, aos patrocinadores, sem os quais a gente, em muitas ocasiões, nós não conseguimos organizar, e, por fim, não menos importante, muito pelo contrário, a todos os voluntários aqui pelo apoio. Que o SBBD 2021 marque não apenas a retomada e a reafirmação do SBBD como a principal conferência brasileira de ciência de dados e Big Data, mas também represente uma ponte para o network, para o brainstorming, e que nos permita a coordenação, organização e realização de ações em torno do tema de banco de dados no presente e voltados para o futuro. O aprendizado de organizar e realizar o SBBD virtualmente tem sido importante para o amadurecimento da comunidade. No entanto, oxalá possamos celebrar juntos, presencialmente, em 2022. Desejo a todos um ótimo evento. A bola está contigo, Eduardo. Obrigado.
Agora, acho que a gente tem que passar a palavra para quem vai coordenar agora a sessão técnica, a palestra convidada, né?
Ok, eu acabei de receber aqui uma mensagem da Karina, eu vou coordenar a sessão, tá bom?
Tá legal. Vou desligar a câmera.
Pois não. Aaron? Aaron? O Eduardo, o Aaron está com a gente já?
Eu tinha autorizado, ele está aqui.
Tá.
I can hear you.
Hello, Aaron. Can you hear me well?
I can hear you. Yes. Can you hear me?
Yes. I'm very sorry, but I'll be playing the role here as the session chair today.
That's fine.
Unfortunately,
That's fine.
Karina was not able to establish a good connection so that she could proceed with this task. But I'd like, on behalf of our community, to thank you very much for delivering this talk. So, ladies and gentlemen, it's my great pleasure to introduce our keynote speaker this year. So, Arun Kumar is an assistant professor in the Department of Computer Science and Engineering and the Halli-Cioglu Data Center Institute at the University of California, San Diego. He's a member of the Database Lab and Center for Networked Systems and an affiliate member of the AI Group. His primary research interests are in data management and systems for machine learning, artificial intelligence-based data analytics. Systems and ideas based on his research have been released as part of the Apache MAD-lib open source library, shipped as part of products from Cloudera, IBM, Oracle, and Pivotal, and used internally by Facebook, Google, Logicblocks, Microsoft, and other companies. He is a recipient of 2 Sigmod Research Paper Awards, a Sigmod Research Highlight Award, 3 Distinguished Review Awards from Sigmod VLTP, the PhD Dissertation Award from UW-Madison CS, the IEEE TCDE Rising Star Award, an NSF Career Award, a Hellman Fellowship, a UCSD OSTEAM Faculty of the Year Award, and research award gifts from Amazon, Google, Oracle, and VMware. So thank you very much, Aaron, again. And please, you can try to share your screen, and it'd be my pleasure to check if everything is okay. Fantastic. So please, if you are ready, we can start. Thank you again.
Okay, thank you, Ricardo. To the audience, hola, boa tarde. That's about my Brazilian Portuguese. Thank you for coming to the talk. And as Ricardo mentioned, my name is Arun Kumar. So Ricardo, I got tenured in the intervening period. Last month, I got the news from my chair.
Fantastic, congratulations. Well done.
Thank you so much. Yeah, the bio, when I sent it, I was still waiting to hear back from the university, but my chair informed me last month. So now I'm technically an associate professor. I need to update the bio. I gave a bio from earlier this summer. Thank you for having me again, and thank you all for coming to this talk. This is great to see the community, the database community in Brazil get together to have this sort of conference. I saw some of the past programs as well. It's a lot of interesting talks and discussions. So I'm really honored to be here. And thank you for listening to what I have to say about what I see as the new DBfication of ML AI. Just a logistical note, if you notice any issues with the slides, feel free to let me know. Ricardo has a copy of the slide deck as well. I just emailed it. So he could also share it from the local internet there in case this wide area global network has some issues. The other thing is I'm presenting from my laptop at home. And if you have any questions, feel free to interrupt me in the middle and post it on the chat. Ricardo, I hope you can look at the chat and let me know if there's any, because I won't be able to see the chat. Okay, let's get started. Okay, it's no secret. Oh, sorry, is there a question? No, I thought I heard someone speak. No, okay, let's get started. It's no secret that we are now in the golden age of machine learning and AI. Pretty much all the major web companies, all the major tech companies are using ML extensively for all sorts of applications in all sorts of domains. This has inspired a lot of demand in various enterprise sectors, things like healthcare, insurance, finance, telecom, retail, and even in the academic domains like domain sciences and even digital humanities, for tools and products that make it easier for them to adopt ML and AI into their data analytics applications. Now, the International Data Corporation, which is a market research firm that studies the data software land, estimates that the market size for these sorts of products is set to hit almost $500 billion US in the next few years. That's an astonishingly large figure, but that's what the IDC estimates. Naturally, there's a lot of activity in this space. There's several open source tools for ML analytics that are widely used. All the major cloud giants are heavily involved in this space, building ML and AI services. In spite of all of this, as I will explain today, as I will share with you today in my talk, there still remain numerous fundamental efficiency and usability bottlenecks in the end-to-end process of building and deploying ML applications. And at the end of the day, that's what my research is about. Devising new abstractions, algorithms, and building software systems to mitigate those sorts of bottlenecks and help democratize ML and AI-based data analytics from a data management and system standpoint. By democratization, I mean precisely the following. Improve the system efficiency, which is reduce the runtimes and the resource requirements of the algorithms and tools involved to reduce the cost, and improve the human efficiency as well, which is improving the productivity of the people involved in the loop, the data scientists, ML engineers, and so on. So my research really unifies and synthesizes upon these areas of data management and database systems with ML and AI, but also straddles the whole system stack. More precisely, in my research, I build practical and scalable data systems for machine learning and AI analytics that are inspired by the principles of relational database systems that we've been studying for almost half a century now. But I also exploit insights from statistical and computational learning theory and optimization theory that are at the root of what ML computations are about. I have interacted with over 36 data and ML practitioners, data scientists, ML engineers, data analysts, business analysts, domain scientists, and so on, in all sorts of applications settings like enterprises, web, healthcare, and even in the academic domains to understand this whole life cycle. And based on my conversations, I distilled this into three major parts: source, build, and deploy. Each of these are iterative processes. In the source stage, the data scientist converts their raw data, like their multi-table relational databases, text corpora, multimedia time series, etc., into what we call ML-ready data sets. Here, they do these processes of data integration, cleaning, data preparation, labeling, and so on. Then you build ML models on the ML-ready data sets. And there you have to go through feature engineering, algorithm search, hyperparameter tuning, and so on. Once you have that, once you've done that, you have a prediction function or a pipeline. That can now be deployed into your application, and that is where they plug this into a data warehouse for business analytics, or plug it into an online application in the cloud or in the IoT setting for live predictions. The data evolves, the application evolves, and so they have to monitor and maintain this whole life cycle and keep the models fresh. Throughout this, they use data systems and ML systems to achieve their goals. Based on these conversations and my understanding of this whole space, this is what I do in my research. I abstract key steps that are bottlenecks for system efficiency or human efficiency, formalize the computations. And by formalization, I mean both the data flow aspects of it and the statistical and ML semantics of it. This allows us to automate some of the manual grunt work that takes place today. And so now they can focus on stuff that they can be more productive over rather than working on manual grunt work. Because we have also formalized the computations, now we can optimize the execution using database and systems techniques that we know and love. And so I've applied this through all parts of the lifecycle. The link down there is my research group webpage here at UC San Diego. And feel free to go have a look at all of our papers and projects that we've been pursuing over the last several years. But for today's talk, I want to talk about something higher level, what I call the new DBfication of ML AI, and then give 2 examples from my research, some of the recent work that I've been up to as part of this DBfication. And then I'll conclude with some thoughts that I have on how we as a community can accelerate this DBfication. Okay, so what do I mean by this? There are several concerns in machine learning that are database-style practical concerns. Now, if you look at the ML community, like the NeurIPS and ICML folks, overwhelmingly they worry about accuracy, prediction accuracy of the algorithms and models they build. Sometimes they also worry about runtime efficiency, typically in the form of whether it's linear time or something else. But in the ML systems world, you also need to worry about several practical concerns for deployment. What if the data set does not fit on your single machine memory? That's the concern of scalability. And it's not enough to be scalable. You also have to be efficient at scale. How are the features and models configured? You have to, like I said, source the data and build the models. That's the concern of usability. How do these tools fit within production systems and workflows? ML is not disjoint from the rest of your infrastructure and production settings. That is the concern of manageability. And people have to build these sorts of tools, and they're called ML engineers, and they're in short supply. We have to make them productive in implementing these, and that is the concern of developability. If you think about all of these have been addressed in the database systems world over the last 3-4 decades, albeit in the context of relational and SQL computations. Now we have to do the same for ML computations. One interesting novel twist here is that ML, because it revolves around accuracy, often you can trade off a little bit of accuracy to gain on one or more of these aspects enormously. And that leads to interesting new research questions as well. Here's another view from industry. This is the hidden technical debt paper from Google that appeared at NeurIPS back in NIPS 2 years ago. Here you see the whole diagram of their ML infrastructure, and the ML code, the algorithms that the ML folks write, is like a tiny little black box in the middle. Around this, you have so many other things going on: data collection, feature extraction, verification, machine resource management, serving, and so on. Understanding all of this and devising principles how these things fit together is what is called the platformization of ML. Now, this sort of platformization of ML is not new. It's been happening for a long time. So it's a brief history lesson here. Since the 80s, the SAS Institute, which is still widely used in enterprise analytics, has been building tools to scale ML to large data. The statistics community started the S programming language, and which eventually became the R programming environment. That has been popular since the 90s among statisticians and many domain scientists even today. But it's only in the late 90s to early 2000s that the database community got involved. We looked at all the data that was sitting in enterprise data warehouses and database systems, and we said, okay, they want to build customer churn prediction models and market segmentation and sales forecasting models. All of this requires machine learning over large data. Why don't we implement these ML algorithms as stored procedures and user-defined functions in the DBMS process space? That led to this suite of tools called in RDBMS machine learning systems. Oracle data mining is a good example. SQL Server, DB2, they also had their own tools. So here they looked at scalability and operating in the DBMS environment. Eventually, in the late 2000s, as the so-called big data revolution took off, people started building these data flow systems that are more general, more scalable and fault tolerant. Hadoop MapReduce and Spark. ML on those environments also became important. Mahout, Spark ML. And people realized that implementing ML algorithms at scale requires a lot of tedious implementation. And so they wanted to build better software abstractions to make it easier to implement these algorithms. That's where these tools like Parameter Server, GraphLab, and also MADLib, Apache MADLib is still around. It's an abstraction and library for ML on Postgres and Greenplum. I was involved with that. All of these sorts of tools came about then. And in the last few years, there's been an explosion of activity in the ML system space. Tree learning systems and deep learning systems have really taken off. XGBoost, IGBM, these boosted decision tree methods are very popular on structured data. And of course, deep learning methods implemented with TensorFlow, PyTorch are very popular on unstructured data. And in the last couple of years, all the cloud vendors, like I said, have started building ML AI services. Like, for example, SageMaker that take into account the end-to-end lifecycle of ML. Google, Microsoft, they all have their own versions. And there's also this trend towards building what are called ML platforms, that are frameworks that can allow you to stitch together these whole pipelines and give you visibility into the whole process, like TensorFlow extended, ML flow from Databricks. And there's also this notion of feature stores, which allow you to materialize transformations of data for ML, like Tecton. So it's really an active space that's rapidly growing. The way I see it, all of this reminds me of the rise of relational DBMSs circa 1980s. That is what it feels like with the rise of these ML systems and platforms. That is why I call it the new DBfication of ML and AI. This involves not just building these sorts of new tools, but also tackling fundamental research questions in all of these three stages of the lifecycle. Let me give some examples. In the source stage, we still have to tackle how do we institutionalize and formalize metadata management for ML? How do we do data preparation and cleaning in a less human-intensive way for ML? Often, people build ML models on multimodal data, fusing different signals from different data modalities. We need to devise query models that can handle multimodal data. We need data search systems when files are dumped on data lakes and there's like very loose schema management. So how do we build better search system to help them find the data they need for their application in the first place? Labeling infrastructure matters. In many cases, it's programmatically labeled. So all of these are data management research challenges in this context. And then on the build and deploy stage, we have a need for scalable data systems for executing ML workloads. And it's not enough, again, like I said, to scale. You also need to utilize machine resources efficiently, processor, memory, disk, network, everything. And that's where query optimization matters for machine learning systems, just like it mattered in the context of relational systems. And now a lot of computations are moving to the cloud. Cloud native has become a big deal. Snowflake had a blockbuster IPO last year. Everybody's saying Databricks is going to have one this year or maybe next. And so cloud native executions, serverless environments, streaming environments, looking at ML systems in those contexts matters too. And because you have this complex end-to-end lifecycle, provenance matters. And if something fails, you need to be able to debug why it failed. Was it the data? Was it the ML configurations? And be able to fix it. So those sorts of infrastructure also matter. And overarching across these entire lifecycle, frameworks that people are building, we need to be able to compare them objectively and scientifically. That requires benchmarking. Just like we've been doing benchmarking in the relational world with TPC and so on, we need benchmarks for all sorts of ML tasks and systems. And it's not just benchmarking systems for runtime efficiency or resource use. We also need benchmark label data for measuring the accuracy of some of these systems. Like, for example, in data preparation and data cleaning, we need to devise benchmark data sets like the ImageNet data set that has had spectacular impact in AI. And all throughout, concerns of fairness, transparency, security, privacy, all of these still remain in this lifecycle. And that leads to a lot of data-related questions as well. So this is what I mean by the new DBfication of ML AI. Let me dive into two concrete examples from my research. What have I been working on in this space? I've done a lot of work on metadata management for ML, data prep for ML, and multimodal ML models. I've also worked a lot on scalable data systems and query optimization at scale for ML, as well as benchmarking of ML systems and frameworks, and building labeled benchmark data sets for data preparation in ML. And so that's two examples that I'm going to share today. Deep dive into scalable deep learning systems a little bit, or work on optimizations for deep learning, and automation of data preparation for ML. Okay, at this point, I'll pause and see if there's any questions. Any questions from anyone? Everything looks good?
Yes, there is a question from Fabio Porto. DBfication seems to cover a lot of functionality than DBMS uses to do. Is there a chance of having a single system for it?
That's a good question. So the way I'm using the term DBfication is DB as a field rather than DBMS as a single system. A lot of these functionalities, it's going to be very hard for a particular software system to do. And even in the database land, we don't have a particular software system doing everything. We have relational DBMSs, we have data flow systems, we have key value stores, we have BI toolkits like Tableau that sit on top of relational DBMSs, we have streaming ingestion services like Kafka. So like that, I think there will be an ecosystem of tools that evolve around this. But the principles and the techniques of how these tools work together, what are their goals, how do we build them better, those sorts of principles that we've been studying in the database world, we need to study in this context as well. So for example, for building and deployment, I think you can build system or a platform like I'm going to be talking about for deep learning. But for tree learning, it's going to be different. You can't build GBDTs with TensorFlow, for example. So that's already a dichotomy over there. Data search system and labeling systems are fundamentally different from model building systems. There are people who are trying to kind of integrate them into an end-to-end pipeline, but they're still separate systems. Okay. Any further questions?
Not up to now.
Okay, great. So let's dive into the first one, scalable deep learning systems. Okay, now put yourself in the shoes of a data scientist or a domain scientist building deep learning models for your task. You specify your training task, you write your what is called neural computational graph in your PyTorch or TensorFlow that specifies your neural architecture, specify the gradient descent process. And then you run it on your cluster. It has a bunch of disks, memory, GPUs, CPUs, excuse me. Maybe it's managed with a cluster managing service like Kubernetes. It sounds nice in theory, but that's not how it works in practice. Because deep learning model building is never one and done. You need to sit and tune these pesky knobs called hyperparameters, tune the architectures, change the data representation to figure out what actually works well for your task, what gives you good accuracy. This is called the process of model selection. This whole process needs to be run efficiently at scale. That's where we started this project Cerebro to understand how we do deep learning model selection efficiently at scale. What do we do here? The deep learning user still interacts with the same tools like PyTorch and TensorFlow, but they now specify this larger model selection process more holistically using APIs that they're already familiar with, things like Keras and others that are available today. There are automated ML heuristics, AutoML heuristics for hyperparameter search that are available today. And so then now you get this bulk specification of a bunch of models to be trained. What Cerebro is a middleware framework that translates the higher level specifications into more optimized executions on the cluster. And here we bring in the magic of what we in the database world called multi-query optimization. We've studied MQO for relational for 2-3 decades. We are the first to bring this in the deep learning context. So fundamentally, what is happening here is that we have decoupled the what of the specification from the how of the execution. We call that physical data independence, logical physical separation in the database world. So we're bringing that to the machine learning systems world. This sort of decoupling means that the data scientist does not need to worry about issues of scalability and parallelism, handling that manually. They only focus on their ML analysis task. The system under the hood handles those details for them. This sort of decoupling also means we can now use the same workload specification on other system environments. Like you can run it in a cloud native fashion, or you can run it on data flow systems or database systems. We've actually integrated Cerebro with Apache Spark already, with parallel RDBMS Greenplum, and we're now working towards a cloud native environment as well. Okay, so what are these sorts of optimizations, and what do I mean by issues of multi-query optimization? I'll give a single example from our recent research. More papers are listed on our project webpage, but this is the first kind of deeper technical paper from this project, so I will walk you through this. This workload is the most common workload in deep learning model selection, things like hyperparameter tuning, architecture exploration. Sometimes it can yield dozens, even hundreds of training configurations for deep learning. You need to tune regularizers, learning rates, dropouts, or number of neurons, number of layers, and so on. You don't need to do it manually. You could specify a grid search or random search that will tell you what configurations to explore, or you could use one of these AutoML procedures that the ML community has devised, Hyperband, HyperOpt, Dasha, and so on. But ultimately, they all lead to the same multi-query workload. There's a bunch of configurations you need to train on a large data set in one go. How do we execute this? We looked at the state of the art. The prior art we found was lacking on one or more aspects. And so we devised a novel execution strategy we call model hopper parallelism, or MHOP. How does it relate to prior art? Brief primer on prior art. Overwhelmingly in the ML world, people prefer this strategy called task parallelism. Task parallelism works as follows. You take your data set D and you copy it across multiple workers entirely. Now you have these different model configs, different hyperparameters or architectures that you want to train. You place one config per worker. Now, each config looks at its local data set alone because the entire data set is available. There's no communication across workers. This is sort of the paradigm taken by tools like Ray from Berkeley or Google's Vizier or Dask and Celery, a bunch of these sorts of tools. This is really good for throughput of model selection. You can train multiple models in parallel. You can finish the model building process faster. And it's really good from accuracy standpoint for stochastic gradient descent. ML theory, optimization theory, tells us you're visiting the data in a sequential order on a worker. It could be multi-core, could be multi-GPU, but you're still visiting the worker on a single node. That converges really well for deep learning training. Obviously, you can see the data scalability aspect, it suffers severely because the entire data set is copied across all workers. So if I were to use a 1 terabyte data set, if you were to run it on 8 workers, it'll bloat to 8 terabytes. So you're wasting a lot of memory, wasting a lot of storage. You can alternatively place the data set on a remote machine and read it repeatedly over every epoch to all workers, kind of like storing it in Amazon S3 and then reading it repeatedly. But now you're traded off wasting storage and memory for wasting the network because these computations are iterative. Stochastic gradient descent, you often run dozens of epochs. Now you have dozens of configurations, your network cost can go up 100 to even 1,000 times. So we are stuck with this. How do we make it more scalable? We know in the database world and systems world, the data parallelism is very scalable. Shard the data. So D is split up into D1 to D3 over here, multiple workers, place one shard on each worker. Now, these data parallel tools like parameter server or Horror, what they do is that each config is trained on its local shard and it exchanges updates either through a server or through each other directly for running stochastic gradient descent. This is very scalable, obviously, because you've sharded the data. There's no copying or no remote reads going on. However, if you exchange these gradient updates only at the level of a full shard, SGD will not converge well for deep learning. It's very slow, so you won't get good accuracy. And so what people do is they communicate these updates between these workers and servers or between workers themselves at what is called a mini batch. A mini batch is much, much smaller than a shard typically. You could have a mini batch size of dozens to hundreds of examples. A shard might have tens of thousands to millions of examples. So you could actually communicate between workers or between a worker and a server thousands of times within just one pass over the data. That leads to very high network communication costs and overall low throughput. Because you're training these one configuration at a time, you're going to repeat this for every configuration and you end up with enormously long runtimes. So we looked at this. We said, can we get the best of both worlds? And that's what we did with MOP. It's a new hybrid of task parallelism and data parallelism. How does it work? MOP is really rooted in an insight from optimization theory that tells us that the stochastic gradient descent process for training deep learning does not care about the order in which you visit the data. It is robust to the randomness. The theory tells us that any random ordering is good to get good ML accuracy. Based on that, we do the following. Shuffle the data, which means you randomly reorder it, partition it across n workers. So you have n models that you can start running on n workers. So this is like the data parallel setting. You have a shard per worker. Now, just like the task parallel setting, you place different configs on different workers. Okay, so this is like akin to running different queries on different nodes in a parallel DBMS. That's why it's the multi-query optimization approach. Each config starts its first epoch in parallel by looking at its local shard. And at the point at which it's seen the entire shard, checkpoint the models, hop them across the workers. And so now you see model 1, DNN1, has jumped from worker 1 to worker 2. At this point, restart the same epoch. So now model 1 sees the shard 2. Keep repeating this process. Models hop across all workers until they see all of the data set. So every model has seen every shard in the data set exactly once. You have finished one entire epoch for all of them. Repeat this whole process for multiple epochs of stochastic gradient descent training, and that will give you the final trained results. This process has strong theoretical guarantees. It's equivalent to sequential SGD, just like in task parallelism, because every model is visiting the data in some sequential order, albeit in parallel. And so you get the same theoretical guarantees of sequential execution. We also showed in the paper that this approach hits the lower bound on communication costs for executing model selection on sharded data. So you cannot really do better than this from an analytical perspective. Notice that the models are hopping across workers only once per shard, not once per mini batch, which means the communication cost of this approach could be 1,000 times, even 10,000 times smaller than things like Horror or parameter server, which are the state of the art for data parallel training. Okay, so this is sort of the basic idea of the model hopper parallelism approach. In database parlance, we call it bulk synchronous parallelism in the database world. This is the first known form of bulk asynchronous parallelism in the kind of systems landscape. Okay, so how do we make this real? This sounds simple enough. There are several challenges to make this a practical idea. We need to build a resource-aware scheduler. We built this for kind of handling evolving deep learning configurations. Many of these AutoML procedures, sometimes they kill certain configurations if they're not accurate. They add new configurations on the fly. Our system can automatically handle all of those. Often you have more configs than workers, so you need a scheduler to place them when the workers become available. We handle that generally with an open shop scheduling with a randomized scheduler. Data replication is supported, so the same shard can be placed on 2 or 3 workers, multiple workers. You can exploit that for fault tolerance. You can also exploit that for more parallelism. Elasticity is natively supported, so if you want to add more workers to increase the parallelism, that is possible. And all of this happens in a non-disruptive manner with existing deep learning frameworks. So your code can still be in TensorFlow or PyTorch. You don't need to change the internals of TensorFlow or PyTorch. Cerebro acts as a wrapper around them and can execute all of this at scale. Any questions so far? So this is one particular technique that is inspired by multi-query optimization in the deep learning systems context.
There is one question from Claudia Medeiros regarding reproducibility. What do you call reproducibility? So,
right, that's a good question. So one thing to note with reproducibility here, what is reproducibility? If you run something on the data set with the same random seed again, you should get the same results. That is the strictest notion of reproducibility. So you're basically, you can even call it replicability if you want. Now, it turns out that some of these systems like asynchronous parameter server, you run it once, you run literally the same thing with the same random seed, you can get a totally different result. Because the way the communication happens across the workers and servers is not under your control. The order is not under your control. The update sequence is not under your control. People thought this sorts of relaxed consistency and asynchrony can help in many of these settings, but here, unfortunately, it can lead to unreproducible results. Okay, questions, more questions. Back in the 90s, people talk about avoid taking data from the da-da-da. Do you think ML services could be provided by database systems even declaratively? So the question is, do you think ML services could be provided by database systems even declaratively? The answer is it depends. For the Cerebro project perspective, I will talk about the approach later. You're actually agnostic to where the data is stored or managed. We support multiple backends. In the DBMS context, we've actually integrated this with MATLAB. I'll talk about that. And you can run it on data resident in a parallel DBMS. You can also run it on data resident in a data flow system or just a regular file system. Our execution optimizations does not depend upon the internals of an RDBMS per se. It's more general than that. Okay, another question, is the approach independent of the parallel machine architecture? That is correct. Yep. This is, again, a purely software level optimization. The underlying hardware of the machine, we are agnostic to that. You could use GPUs, you could use FPGAs, you could use whatever you want for the processing. And same for storage and networking. Last question, what if the model does not fit in memory? Great question. We actually have a new paper, new technical report out that actually addresses this exact issue. The model sometimes may not fit on your GPU memory. In that case, we actually have an approach that shards the model and hops the model around across GPUs. So it's an analog of model hopper parallelism, where instead of this small model, large data regime, you have this large model and likely small data regime. You can put the two together, both models and data sets can be sharded and hopped. Okay, I'm happy to send more references or chat more at the end. Thank you. Okay, more questions? Great, let's proceed then. So how does this work? So there's a bunch of experiments in the paper, the VLDB paper that appeared last year, but this is sort of a headline result. Standard ImageNet benchmark workload from Vision. So it's like large data set. We trained 2 different CNN architecture state-of-the-art and 8 different hyperparameters each, 8 GPU node cluster. Standard TensorFlow. This is the learning curve that shows the top 5 validation error, that's the benchmark metric, against the number of epochs of SGD training. Model averaging, which is the bulk synchronous processing paradigm, which converges very poorly because it communicates SGD updates once per epoch. Hot avoid, which is this mini batch parallel setting, converges well. TensorFlow parameter server actually converges even better because of the mini batch cap, but Hoverboard can also do the same. Celery is a task parallel execution system where you copy the whole data set, you place different configuration on different workers. Cerebro converges almost the same as the task parallel system. So you get same learning behavior as your task parallel system. But if you look at runtime and memory, the system metrics, parameter server synchronous is almost 10 times slower than Cerebro. Hoverboard is almost 3 times slower. Model averaging, of course, doesn't converge. Celery and Cerebro have roughly similar runtimes. But if you look at the memory footprint, Celery is 8x the memory footprint for the execution of this workload because it fully replicates the data set. Overall, if you put all machine resources efficiency together, processing, memory storage, network, and ML accuracy in the mix, Cerebro offers the overall best combination of these. In the paper, we have more experiments drilling into each aspect, more AutoML benchmark heuristics, and so on. Okay, so that's the model hopper parallelism technique. We are going all the way to all sorts of model building workloads in deep learning. You can specify these. The Cerebro system is actually a layered platform where you can specify a model building at a higher level using these APIs that they're already familiar with. Hyperparameter search architecture. So it's transfer learning, ablation, building separate models for separate groups. And you could do this in your command line interfaces. You're building a graphical user interface. You could do it from your notebooks. Under the hood, we are agnostic to the execution and storage layer. Cerebro does not care where your data is sitting. It does not care what machines you're using. You can directly access the file system. You could use a cluster manager like Kubernetes. You could use data flow systems, data flow engines like Spark. We've already integrated with Spark and Greenplum as well. You could also run natively on cloud infrastructure. And so Cerebro will support all of these. Our secret sauce is really in the middle, the optimization and scheduling layer that takes the what of the specification and converts it to an optimized how of the execution. This is where our hybrid parallel techniques like model hopper parallelism and several others we have recently published, materialization management for transfer learning, these sorts of techniques we've published too, will all be implemented. And they are all implemented as wrappers around TensorFlow and PyTorch. So for things like automatic differentiation, stochastic gradient algorithms, we don't need to re-implement those. The compilers for the neural computational graphs, we don't need to re-implement those. Hardware architectures, we are not tied to any particular processing hardware. So if TensorFlow and PyTorch were to evolve tomorrow to a different compiler, Cerebro will be backward compatible. It's just a drop and replacement. So that's the architecture we built. On the side, all metadata for the models produced or managed will be managed using tools, off-the-shelf tools like MLflow. You could visualize the model building process using TensorBoard, an integration that we've done with our GUI. All of this is fault tolerant and elastic as well. Oh, there's a question? Okay, that's not a question. Best student question will gain an SBBD t-shirt. Wonderful. T-shirts, yes. I remember when we got t-shirts from conferences. Now they don't send it anymore. Okay, so Cerebro, like I said, is a model selection first platform. It's the first of its kind where we are focusing on model selection first design for scalable deep learning. It allows you to specify these processes at a higher level and automatically infuses multi-query optimizations, materialization optimizations that we know and love in the relational context, but now reimagined for the deep learning context. This allows for better resource efficiency. We can push processor utilization much closer to 100%. We could reduce bloats and wastage of all sorts of machine resources. And it ensures the productivity of the deep learning users because they focus on what they want rather than issues of system management and scalability and so on. I'm happy to say Cerebro is being already used by our collaborators in public health here at UC San Diego. They have terabytes of labeled accelerometer time series data for understanding people's exercise behavior. We've been working with them for 3 years now. We publish some of this from our public health journal as well. We're also talking to computational physicists, materials engineers to look at other issues across the stack for scalability. Like I said, MADLib has adopted this and they have shipped it. Pivotal has shipped it. VMware is now putting it in front of enterprise customers. We've also open sourced all of this with Apache License 3.2.0. You can check the website for the documentation, try it out and let us know what you think. We welcome feedback. More workloads, optimizations, and use cases in the domain sciences are in the works. I'd like to thank all these agencies for supporting this project. More questions on the chat?
Yes. What is the role of metadata manager? You showed your figure.
Yes. So the metadata manager is basically when you're building these sorts of multiple models and doing a lot of feature transfer and transfer learning and stuff, you need to know what is what. That's pretty much what it is. Now, we don't need to reinvent the wheel there. Tools like MLflow already support these sorts of metadata management and governance functionality. We are just plugging Cerebro into MLflow so that you can reuse those sorts of components. So now, if you want to visualize this particular, say, one particular model among the 20 models that you build, you could easily specify that using your APIs for model cataloging, for example. Okay. Data preparation also parallelized in this workflow. Good question. So far, we are not looking at data preparation in the deep learning context here. Anything that involves the neural computational graph, that is where Cerebro starts. This is the reason we are integrating it with these data flow engines, Spark and Greenplum and so on. They are really designed for scalable data preparation. So if you have your, say, a bunch of time series data sets and you need to chunk them somehow, Spark already has their data frame API that can do that for you. So we don't need to, we're not looking into kind of reinventing the wheel there. Okay. Great, thank you. Let's continue. Are there any other questions? If not, we can continue.
You can continue.
Okay, thanks, Ricardo. Okay, so that's just a sample of the scalable deep learning systems work that we've been up to that are inspired by lessons from the database systems work, but kind of reimagining it and building something new in the ML world. Next, I'll briefly touch upon our other work in the sourcing stage of data preparation, automation, and ML. Now, a lot of ML service providers and cloud vendors are claiming that they've automated data preparation. Now, we know data preparation is this labor-intensive process. We've been studying that for 2-3 decades now. But like, for example, TransmogrifAl is a library from Salesforce Einstein, which claims that they've actually automated this data transformation for ML. SageMaker, Autopilot also claims they automatically transform the data. You just need to load a CSV and model will get built automatically. TensorFlow Extended and Google's platforms internally also are moving towards that direction. So the abstraction is these end-to-end AutoML platforms. Just upload a table from your database or data warehouse or file system. It'll take care of everything for you, all the way and build your churn prediction model or sales forecasting model. I looked at this and I was suspicious and I was like, just how good is their automated data preparation? No one knows how good it is objectively. So they're just walking in the dark. And that's where we decided to set about creating benchmarks for machine learning data preparation in Project Sorting Hat. The vision is published in Sigma Dean workshop, but basically the notion of a benchmark for data prep and ML, what does it involve? We saw 3 components. One, we need to formalize what the task is. What is it that is going as input? What is it that's coming as output? What is the semantics of the data prep task? We need to understand accuracy of these automated procedures. And there we need labeled data sets, input-output pairs to assess the accuracy of data prep. And it's not enough to just look at the data prep step. It's in service of ML model being built in the AutoML platform. Does your data prep step really help the ML model that's being built? That's called downstream prediction. So you need to assess the accuracy of that too. So we saw these 3 components as essential for benchmarking ML data prep. From a deeper scientific standpoint, there is this question of how does ML data prep actually affect ML accuracy? Why are data scientists doing all these transformations? How do they know it's actually helping their accuracy? Sometimes they do stuff and it totally doesn't help accuracy. So they're wasting a lot of time. And in the AutoML context, these platform developers are interested. Suppose the data prep step fails, it doesn't work accurately. Are there fail safes that we can build so that their downstream accuracy is still not affected? Maybe by trading off more runtime for something. So these are sort of some scientific questions we're asking. Fundamentally, data prep affects the bias variance trade-off that's part of learning theoretic understanding of what ML accuracy is in exactly the same way that feature engineering, algorithm search, and hyperparameter tuning affect it. But nobody has looked at it from this sort of a standpoint, and that's what we're looking at. Now, what are sort of the tasks in our data prep benchmarking effort? We call this the ML data prep zoo. We have formalized a set of tasks, and we wrote about it in the vision paper. So far, we have benchmarked the first task and this task 0 and task 2. This is by no means comprehensive. Data prep is probably dozens or even hundreds of tasks involved, but we saw based on our study of these AutoML platforms and talking to practitioners, these are some of the common steps that need to be done in these platforms. And so you need to study their accuracy because they can affect the downstream accuracy significantly. Like for example, task 0, ML schema inference is the very first step. You uploaded your database file. Let's say you exported from your database as a CSV file. Zip code is an integer, of course, in your database. But now in your AutoML tool, if you give zip code as a number to a model like a logistic regression model, it's going to give garbage results. Zip code is not an integer. for your ML model. It needs to be cast as a categorical, which means it's a discrete set. So the AutoML schema needs to be figured out, and that can be done automatically. We showed that some of these existing procedures for doing it automatically that are rule-based fail catastrophically in many settings. And we built benchmark label dataset for this. We trained ML models based on our data, and we showed that that boosts accuracy substantially. So we've been doing this for a bunch of these other tasks as well. And we've been collaborating with Google as well. They were very interested in some of our internal kind of models that we built, the label data that we built. The TensorFlow data validation team as part of TensorFlow Extended is looking into adopting some of our schema inference models, and they are testing it on their internal AutoML benchmarks as well. We also had a project for catalog search of models and dataset artifacts that is going to use some of these models. AWS is also starting to collaborate with us to understand how they can use this in some of their SageMaker and Redshift products. OpenML, which is a community repository for sharing data and pipelines, they're also interested in adopting the schema inference models. So I think there's a lot more work to be done in this benchmarking of data preparation for ML space, and that can have immediate impact in many of these settings. Okay, so that's about it. Just a sample of 2 pieces of work from my group, but this overarching picture is really bringing in the principles, the concepts, the techniques, and the tools that we've been building for the relational SQL context to the ML and AI context, and that's what I call the DBfication of ML and AI. Leaving these sorts of problems open will lead to a huge waste of time, effort of these practitioners, money, energy by these companies, all of these people who are using ML and AI intensively. And it is high time for the database community and the ML and AI community and other areas of computing to join forces to accelerate this DBfication of ML AI to help democratize ML and AI. That's what I'm going to be talking about last briefly, probably just 2-3 minutes. I think we're almost towards the end of the talk, and then we can take more questions. How do we accelerate the DBfication of ML AI? Now, of course, this is a database conference, so I'm sharing my thoughts to a database audience on what I went through when I kind of looked at this space. Hopefully this is helpful. This is not comprehensive, but hopefully this is helpful. Wait, there's a question on the chat. Okay, there's a question about the data preparation stuff. Have you tested this data preparation in all the domains you mentioned for MOP? How do you know this is not sort of like outliers? So the MOP stuff was in the context of deep learning execution. This data prep stuff we're looking at in the context of AutoML platforms or tabular data. There are 2 different projects here. We haven't really looked at issues of outliers in the data prep so far, because people have already studied the outliers issues intensively in the statistics and data mining and data cleaning world. We're looking at certain tasks that these AutoML platforms are automating that have not received as much attention. So we wanted to focus on stuff that is actually missed and that's new. Now, of course, outliers, there's already some benchmarks out there that people can reuse. So that's sort of why we didn't prioritize that. There are several other such tasks that people have already studied. And so in the future, people can potentially contribute these sorts of other benchmarks into this zoo as well. This is a community repository. It's open source. Everything is on GitHub. Our data or models are on open source on GitHub. People can contribute to these benchmarks as well and make them grow. Okay, great. So let's get back to this acceleration of DBfication part. Now, this is just my thoughts. If you are from a database background, how do you kind of contribute to this? First thing I would say is learn the fundamentals of ML and AI algorithms, and if needed, ML theory as well. This is kind of like learning the basics of logic and relational algebra and SQL if you want to work on relational DBMSs. So we could do this with an ML algorithms class in your institution or even online. There's a lot of good courses also. Some of the books that I referenced was Hastie, Tibshirani, and Friedman from statistical ML, Tom Mitchell for other ML algorithms, and more recently, Bengio, Kurville, and Goodfellow for deep learning. These are really good books to get and have as reference. And you don't need to learn everything up front. Depending on what system and what problem you're studying, you can learn the specifics. If you're working on deep learning systems like Cerebro, you need to understand deep learning properly, stochastic gradient descent. If you're working on accuracy trade-offs like the data preparation stuff you're talking about, you need to understand what is the bias variance trade-off, how does hypothesis space work, what is the complexity of the hypothesis space, and so on. You could start with a graduate course that people have created in this space. And of course, this is my talk, so I'm going to plug my course. The Data Systems for ML course that I created at UC San Diego, I've been teaching for 5 years now. And it's all the materials are publicly available from last year's edition. All the videos, lecture videos are on YouTube, so you can have a look at it. A lot of folks from around the world have dropped me thank you notes from Europe, from Africa, from Asia, and so on. Even folks from Google sent me thank you notes for making these sorts of course materials public. They kind of understood the space of ML platforms better after looking at this course. So feel free to have a look and let me know what you think. I also wrote a research book in this space, the first book on machine learning systems, data management ML systems, with my colleagues Matthias Bohm and Jun Yang. It's available for free on academic networks from Morgan and Claypool, so feel free to take a look at that as well. It gives you an overview of the entire landscape that I talked about and specific research questions and open questions in this space. There are several tutorials, and of course, lots of papers now in this space. Sigmod and VLDB are now active venues where DBfication of ML is being published. These are some of the tutorials that I picked that are really good for you to go look at. And then you can follow the references there for specific problems or areas you want to dive into. The data management for end-to-end machine learning workshop is a really good place to go and network and learn about the area, about the state of the art. Human in the loop data analytics, Hilda, is also a really good workshop I recommend. There's this new conference called MLSys that has come about recently. It kind of brings together several communities, 7 or 8 communities in computing to look at ML systems, and that's also a nice venue worth checking out. Attend these panel discussions on this DB for ML stuff that go on once in a while. I myself was involved in running these panel discussions. This one was at the Dean workshop in 2018. I wrote a blog post about it at the Sigmod blog. It's one of the widely read blog posts. It was a lot of fun. I did another panel discussion earlier at Sigmod this summer, and that was also a lot of fun. The video is, I think, up online, but I'm going to post a blog post on this also. So keep an eye out for it. But most importantly, it's not just about doing research and publishing papers. Also speak and collaborate with actual ML users. Build real stuff and help transfer research to practice so that you learn from it and then complete the loop. Practitioners come in all sorts of forms. Data scientists, data analysts, ML engineers, ML ops engineers. They could be in all sorts of settings. They could be in domain sciences on campus. They could be in enterprises, web companies, cloud vendors, policy folks. Create open source artifacts. Release your software as open source tools that people can download and try out. Release the data sets that you create so that people can share and standardize things. And this is something I've also done, which is not just attend research conferences like Sigmod VLDB, but also go to some of these industry conferences that are widely attended by some of these data and ML practitioners, like the Spark AI Summit. I went to the Strata Data Conference a couple of years ago. One of my collaborators presented Cerebro at FOSDEM, which is for open source developers. And later this year, I'm also attending the Open Data Science Conference. And this is kind of a good venue for me to interact with these sorts of practitioners, learn about other new bottlenecks, emerging problems, and also help translate some of my research to practice. Now, publications in this space, it's not just the regular research tracks. We've also launched the scalable data science research category in VLDB last year. I was involved with shaping this, and I was one of the inaugural associate editors. I'm sticking around for the second year as well as an associate editor for SDS. So been exciting. We're going to release a blog post about how SDS went in the first year as well. So keep an eye out for that. It's not just VLDB. Sigmod has something similar. MLSys, of course, I already mentioned. And of course, KDD has also had the applied data science track. These are sort of top tier publication venues that you can send some of this work to get published. So overall, I hope the database community steps up to this grand challenge of DBfication of ML AI to help democratize ML AI. Partner with folks in ML systems at HCI, work with actual users in domain sciences or industry to help translate our research to practice as well. That's a wrap. I'd like to thank all these terrific students here at UC San Diego. I've been really fortunate to work with such amazing students. Supun and Raj are graduating this quarter or next quarter. I also have a couple of students joining us. You can have a look at their webpage. Also, links are available on my group webpage down there. And I'll stop here and I'll take more questions. All papers, blog posts, doc videos, code, demos, everything is linked from our project web pages on the group webpage. And feel free to check it out. Shoot me an email if you'd like to connect on anything specific, or feel free to follow me on Twitter if you want more research updates sooner from my group. I'd like to thank all the other sponsors of my group's research as well. So I'll stop here and I'll take more questions.
Thank you very much, Arun. Fantastic presentation. So we have time for more questions from the audience. Any further questions?
This was great. The audience was pretty active and lively. It's great to answer a lot of questions.
There are 2 questions posted right now. So do you think there is still a big gap between research proposals and what is used in the industry? And the other one, what is the impact of online inference on ML optimization?
Okay. So the first one, do you think there is still a gap between research proposals and what is used in industry? The answer is it depends on what aspect you're looking at. A lot of the stuff in the sourcing stage, they're still in the research domain. On the build and deploy stage, some of these tools are already getting deployed. So the gap is starting to narrow. Much of the research on the deploy stage is actually happening in industry, not in academia. Things like feature stores, ML ops, model monitoring, a lot of this is happening in industry because academics don't get exposure to cloud native ML applications. Most academics are not running giant applications that are used by millions of people around the world. It's the tech companies that are running, the web companies that are running these. So some of this deploy stage research is happening a lot in industry. I think, yeah, there's a whole spectrum of problems where some are earlier on in the research, some are closer to deployment, and some are actually in deployment already. Okay. What is the impact of online inference on ML optimization? Oh, okay. So online inference, by that, do you mean online kind of deploying the models on the cloud native and optimizing it there? Can you clarify? Oh, on streaming data. Okay, got it. So streaming data is another challenging setting. As far as I know, most companies don't operate streaming ML infrastructure in production today. AWS has SageMaker that is actually a streaming implementation. There are some companies I've heard in China that are moving towards kind of real-time streaming-based implementations. There is a lot of ML heuristics and algorithms studied that port these ML algorithms to streaming data for incremental processing. So they can be deployed in some of these settings as well. By and large, the training process of models still happens in a batch-oriented setting. That's what I'm finding. Inference, which is the deployment of a prediction function to do predictions on live data, that does happen in streaming infrastructure a lot because they need to happen in real time. Often on websites, people click and then you need an immediate prediction. It needs to be tens of milliseconds latency. Internet of Things devices, again, it happens in a streaming fashion, but it happens on the device. So you have to do deployment on devices and heterogeneous environments. People are also integrating inference with database systems and data warehouses for doing inference as part of SQL queries as well. So I think there is this rich space of online inference on streaming data and in kind of other real-time contexts. Okay, that's also an interesting. I haven't studied much of that space though, because I don't have access to these deployment environments. I like to work on real problems with real data, and most of these deployment environments are only available in industry.
Yes,
okay.
Thank you very much. Any further question from the audience? There is one from Mirella. I'd like, of course, to acknowledge Cláudia Medeiros, Jéssica Costa, Fábio Porto interacting with us through the chat. Any tip on how to do research on database plus ML AI with limited resources, especially in Brazil, where most research groups do not have the same investments as big multinational companies?
That's a good question. That's a question that all academics ask all over the world. It's not just in Brazil, I can assure you. One thing I like to kind of tell folks in the space is we don't have to compete with big tech. We don't have to compete with the Googles and the Facebooks of the world. As academics, we have much wider canvas. We can look at problems that are getting less noticed and less appreciated in some of these big tech companies. I call this the problem of plenty. So there's another talk on Cerebro that you should check out on my group webpage, where I call these cloud whales or these tech whales. They have so much resources that sometimes they just ignore a lot of problems. So like the query optimization for ML stuff, it really started in an academic cluster environment because we were having this cluster on campus. It was a shared cluster. Googles and Facebook can just throw dozens, hundreds of GPUs at the problem. So when we think about these sorts of limited resource environments, that can lead to new creativity, new kind of ideas that we've already studied in the database world and then kind of reimagining that in the ML world. Another opportunity is in the sourcing stage. Most of the computations are not expensive. They're more kind of human in the loop or kind of manual labor intensive kind of stuff there. We could do a lot more stuff, algorithmic work, tool building work that doesn't involve expensive resources. So the closer you get to deep learning executions and deep learning model building, the more expensive resource costs become. Some countries do have public infrastructure. Like here in the US, the NSF has funded this cloud infrastructure called Cloud Lab. That is what we've been using in my group for a long time. UCSD also has this on-campus cluster. So the university invested in a GPU cluster that's shared among all the faculty and courses and stuff. So it is possible for some universities to mitigate this. It's possible for government to enable these sorts of scientific infrastructure. Hopefully more people will take notice of that and make it possible for academics to benefit from this. Some of these big tech companies also offer cloud credits. They're very competitive, unfortunately. They give very few people, but they do offer cloud credits as well. So you could run this on the cloud for a few $1,000s or something like that. Okay, hopefully that is helpful.
Yes, thank you very much, Aaron. There's one final question. I don't know if I got what Jessica means, but is there a difference between using or not using parallelization when dealing with real-time forecasts?
Okay, so by real-time forecast, you mean, again, related to the online inference question, the streaming infrastructure? Is that correct?
I think so, but I'm not sure.
Okay.
Yes.
So, okay, thanks. So it depends on the access patterns and the computation, what is called arithmetic intensity of the workload. If you're doing deep learning inference, parallelization certainly matters because the tensor computations that take place in a neural network is very arithmetically intensive. And so what people have been doing is actually building hardware accelerators for deep learning inference. It's an entire cottage industry. There's like tons of startups in this space where they're just building new chips for accelerating and parallelizing deep learning inference. In fact, Apple, I have this iPhone with me that has a TPU, that has a tensor processing unit, not the Google TPU, it's a different tensor processing unit, because for identifying faces or emojis and stuff like that, they actually have an accelerator there. Now, if you're talking about multi-node parallelism, that is probably less critical for kind of real-time forecast and real-time inference because communication costs can kill you. Often these real-time applications, the latency requirements are very stringent. It's like tens of milliseconds. And so the trend has been from the computer architecture and compilers world to move towards specialized processors for inference. Now, that said, many companies still run inference on regular CPUs and regular compute infrastructure as well. Facebook has this nice paper at HPCA a couple of years ago where they profiled all their applications, ML applications at Facebook on their newsfeed, face recognition and stuff. And they said which one runs on GPU, which one runs on CPU, what is the scale of the data, what is the frequency of updates, is it real time, is it not real time? Turns out that many of their ML tasks are not real time, some of them are, but most of them aren't. And many of their ML inference still runs on CPUs. Why? Because GPUs are reserved for training deep learning models. CPUs are sitting around idle, they utilize that for a lot of inference. So it's a very interesting paper, I'd recommend that.
Thank you very much, Aaron. So once again, on behalf of our community, I'd like, to thank you and congratulate for this, achievement in your career, and yeah, to wish all the best, and stay tuned, for future interaction with our community. I'll be glad to explore opportunities and put you in contact with many members of our community. Thank you very much again. And I'd like to thank you all attendees of this session. And I do wish that you may enjoy, the remaining sessions of this conference. Thank you very much. Have a nice afternoon, everybody. Thank you.
Thank you all for coming, and thank you for the wonderful questions and the interactions. I enjoyed this. I'll enjoy the rest of the conference, and all the best, and stay safe, everyone. Thank you again for having me, Ricardo, and happy to connect with folks offline, happy to connect at a physical conference once we get back to in-person. The last one, I remember, I actually visited Rio de Janeiro in 2018, VLDB, had a lot of fun there. We spent 2 weeks there. I'd love to visit Brazil again.
Yes, sure. Yeah. Thank you.
Do you want to take a picture with everybody?
Oh, yeah, sure.
Oh, yes, sure. So please open. Yeah. Turn on your camera. Okay, you can collect some screenshots, Eduardo.
1, 2, 3. Okay, so next window. 1, 2, 3. That's perfect.
Okay.
Okay. Thank you very much, everybody. See you soon in the next session.
Take care. Bye.
Bye-bye.